Hi there and welcome back, and we'll do our fourth sample problem for this topic, and this one is taken from the textbook by Philpott, Mechanics of Materials, and this is example 2.1. Okay, so I chose this sample problem because this involves equations regarding the geometry of deformations. Okay, so remember the rotating rigid bar. So we will need additional equations coming from the geometry of deformations. Okay, so the problem says a rigid bar is pinned at A and supported by two steel rods connected at B and C as shown. So right here we have this rigid bar. Okay, so this is our rigid bar, and we have the steel rods 1 and steel rod number 2. And here is a pin support at A. And this is B, this is C. Now it says here that there is no strain in the vertical rods before load B is applied. So when this load is not yet applied, there is no strains. Now after the load B is applied, the normal strain in rod 2 is 800 micro strains. Okay, so once the load is applied, then there's gonna be a deflections right here, or a strain value, not a deflection, so a strain value of 800 micro strains. So determine the following. Okay, so determine the following. First is the normal strain in rod 1. Okay, so this one is given in terms of strain, but the geometry of deformation must be expressed in terms of deflections. So once you have all this, you can solve for and also once you apply the equilibrium case, then we can be able to solve the deflection. What's going to be the deflection at this point B, right? So it's like this. There's a rod, so because of the load it goes down. So right here there is a strain value of 800 micro strains, and what's going to be the deflections or the strain right here at point B. Okay, so first is let's sketch the deformation. Sketch the deformation. Okay, so right here we have a deflection. Let's just write deflection at C, which can be obtained by using this given strain value. Right here, let's write this is deflection at B. Okay, so we also have, let's write here the distance. So right here, this is 2.0 meters, and right here, this is 4.5, because 2 plus 2.5, so this is 4.5 meters. Okay, so just by similar triangles, then we can obtain the geometry of deformation. So therefore the geometry of deformation, or I think, okay, so from the geometry of deformation, okay, we obtain the compatibility equations from the geometry. Okay, so this is just simply delta B. Okay, so since they have the same angle, so it's just simply delta B. Delta B. So delta B all over the length 2.0 is equal to delta C all over the length of 4.5. Okay, so what's next is solve first for the deflection at C. So recall that the strain equation is just simply at C is equal to the deflection at C all over L, right? And this is the strain at C times L. Okay, so delta C is equal to 800 times 10 to the negative 6 times the length of 2,700. This is let's express this in terms of millimeters. It's actually, if you express this in terms of meters, then I mean the deflection usually is just small, so typically it's just expressed in mm, so 2,700 mm. So this is 2.16 mm. Okay, so once you have this, then solving now for delta B, okay, using this equation. So let's say this is equation number 1. Using equation 1, right? So delta B is just delta C times 2.0 divided by 4.5. Okay, so what you get here is 0.96 mm. Okay, so the value also makes sense because this one is larger than the deflection at B. Okay, so therefore, right, so therefore, what else? Therefore, the strain is strain at B is what? So it's just simply the deflection at B over the L, and this is 0.96 over 1,500 mm. This is equal to 640 micro strain. Okay, so the next is when solving for the letter B. So for letter, for letter B, so let's draw our sketch. Our deformation. So sketching now the deformation for question B. So it says here the actual normal strain in rod 1 is if there is a 1 mm gap in the connection between the rigid bar and the rod 2 before the load is applied. Okay, so we are to find the normal strain if there is a gap right here. So it's like instead of beginning straight or beginning flat right here, we have a gap already, right? So it's like we have this gap. So this one is 1 mm, right? So from this initial point to that, that's 1 mm, and this one will be the deflection at C. Okay, so right here, this is the deflection at B. Okay, and if we have this dimension, this is 2.0 meters, then this one is 4.5. So for the equation, we have the delta B all over the distance 2.0 is equal to the delta C plus the gap. That's the 1 meter, because it's already given all over 45. Okay, and this delta C is actually the same value as the ones we used in question A. Okay, so therefore this delta B is 2.16, right? 2.16 plus 1 mm, right, times the ratio of the length, 2 divided by 4.5, and this is I think this is 1.404 mm. Okay, and therefore the strain, okay, the strain is simply the deflection at B all over L, and this is equal to 936 micro strains. Okay, so just to have a review, actually what we're solving here is not the displacement of this rigid bar, but rather we relate this displacement of rigid bar in the deformation of this in the strain of this rod 1 and rod 2. Okay, so we just obtained that from the geometry of deformation. Okay, so first what we did is we sketched first the deformation, because if you recall in our lecture handouts that okay, so we can obtain the geometry of deformation depending upon the class of problems that we have. So we have here the axial members connected to a rotating rigid element. So this is it actually, and we have this this guide for deflections, or I mean for the compatibility equations. Okay, so we draw first the deformation, and then we apply the principles, and then we solve for the strains, because the strain is related to the deflections, so you can obtain the deflections of B as well, the strains. Okay, so if it has a gap, then you just simply add the gap clearance right here. Okay, so I think that's all for this axial members, and I'm still not sure if we still have to do a lot more problems on statically determinate, like for example this one for coaxial or parallel axial members, or axial members connected in series. Okay, so I think that's all. So see you in the next lecture.